Assalamu alaikum, dear students of Standard 12. How are you? Hope you all are fine by the grace of Almighty Allah. Dear students, in the content, I set a picture where we are seeing students are showing victory sign after passing HSC examination successfully. And you are the HSC examinee for the next year, and I hope you will also successfully pass your HSC examination and will celebrate like them by showing victory sign. So that's why I set this picture for you today. So now welcome back to my physics class. Dear students, this is the last class of magnetism, and today's topics are we will discuss about magnetic materials and hysteresis loop. So let's start the class. Magnetic materials are of three kinds: diamagnetic materials, paramagnetic materials, ferromagnetic materials. So now I will discuss diamagnetic materials. Diamagnetic materials are those that some people generally think of as non-magnetic and include water, wood, most organic compounds such as petroleum and some plastics, and many metals including copper, particularly the heavy ones with many core electrons such as mercury, gold and bismuth. So you must memorize the examples of all these materials. Here you are seeing the diamagnetism. So the properties of diamagnetic substance: diamagnetic materials repel magnetic lines of force. There are no permanent dipoles. Consequently, magnetic efforts are very small. Generally, the value of diamagnetic susceptibility is independent of temperature and applied magnetic field strength. Here, the examples of diamagnetic substance. So, diamagnetic substances are those substances when they are placed in a magnetic field, they get weak magnetism in the opposite direction of the magnetic field. Now, I will discuss paramagnetic materials. These are metals that are weakly attracted to magnets. They include aluminum, gold, and copper. The atoms of these substances contain electrons, most of which spin in the same direction, but not all. This gives the atom some polarity. Look, in absence of magnetic field, the atoms are haphazardly scattered. But when the magnetic field is applied, then they are arranged in a particular direction, but not all. That's why it gives some polarity. So the properties of paramagnetic materials. Paramagnetic materials experience a feeble attractive force when brought near the pole of a magnet. These materials possess some permanent dipole moment which arise due to some unpaired electrons. The magnetic susceptibility, this symbol is known as chi, is small and positive. Example of paramagnetic materials: platinum, aluminum, copper, sulfate, etc. Here you are seeing paramagnetic materials are attracted by a strong magnet, but diamagnetic materials are repelled by a strong magnet. Now, ferromagnetic materials. Ferromagnetic materials are those materials which exhibit a spontaneous net magnetism at the atomic level, even in the absence of an external magnetic field. When placed in an external magnetic field, ferromagnetic materials are strongly magnetized in the direction of the field. So the substance, when they are placed in a magnetic field, they get a strong magnetism in the direction of the magnetic field, are called ferromagnetic substance. When a ferromagnetic substance is placed in a external magnetic field, then the magnetic field inside the ferromagnetic substance increases many times. If a ferromagnetic substance is placed in a non-uniform magnetic field, it rapidly moves from weaker area to stronger area. Look, in the magnetic domain, the magnetic dipoles are haphazardly arranged, scattered in different directions. But when a strong magnetic field is applied, external magnetic field is applied, then in each domain, the dipoles are arranged in a definite direction. Now, look, ferromagnetic materials. Below Tc, spins are aligned parallel in the magnetic domains. Tc means Curie temperature. Here I have to explain what is Curie temperature. When temperature crosses a definite value, ferromagnetic substance loses its magnetism. This temperature is called Curie temperature. So, below Curie temperature, spins are aligned parallel in the magnetic domains. And when it reaches to the Curie temperature, it loses its magnetism. Antiferromagnetic substance below Tn, that means nil temperature. Tn means nil temperature. And what is nil temperature? I think I have to make you clear about it. The magnetization becomes maximum at a critical temperature, which is known as nil temperature, and that is denoted by Tn. So below Tn, spins are aligned anti-parallel in the magnetic domain. Ferrimagnetic, so they will cancel each other's effect here. And ferrimagnetic substance below Tc, that means Curie temperature, spins are aligned anti-parallel but do not cancel. Okay. That's why a small magnetization appears in the direction of the field. Paramagnetic substance. Spins are randomly oriented. Look, randomly oriented. So, types of magnetism. Look here. Ferromagnetic substance possesses net magnetization. Ferrimagnetic substance possesses net magnetization, and paramagnetic substance. But no net magnetization, that means M equal to 0 where diamagnetic substance and antiferromagnetic magnetic substance. Okay. Dear students, now I will explain an interesting thing, that is hysteresis loop, and which will shows the relationship between the induced magnetic field in magnetic flux density B and the magnetizing force H. It is often referred to as BH loop. An example of hysteresis loop is shown below. Look at the figure. In this figure, look, this curve is looking like the loop. That's why it is known as hysteresis loop. Here along x-axis we applied magnetizing force, and along y-axis we will plot magnetic flux density. So here this graph shows the relation between magnetizing force and magnetic flux density, and here the magnitude of B change, how the magnitude of B changes with the with respect to magnetizing force H, that can be shown in this figure. Here B is the magnetic field inside a ferromagnetic substance, and H is the magnetic field, magnetizing field. Okay, here B is the magnetic field intensity inside a ferromagnetic substance, and H is the magnetizing force. Okay, so at the beginning, the sample of the ferromagnetic substance is not magnetized, and it is denoted by the point O, that is the origin. So at the beginning, the ferromagnetic sample is at the origin, where there is no net magnetism. Okay, with the increase of H, with the increase of value of H, the magnitude of P will also increase, and at point A it becomes saturated. So above A it will not increase. So then if we decrease H to 0, then we will see, I think you can think that if H is 0, then B also tends to 0. B will reach to 0. But here we will see that is not happening or occurring. So when H becomes 0, that means magnetizing force is 0. But we will see the magnetic flux density will decrease to somewhat, but not becomes 0. So this phenomena is known as retentivity. That means here some magnetism still remains. So this is shown here at this point B. The magnetic field which remain in the sample is called remanence or retentivity. Okay, the magnetic field which remains in the sample is known as retentivity. Now, to bring the value of B 0, look, when B reaches to C point, then the value of B will be 0, but we will see the magnetizing force H will increase in the negative direction. Okay, that means negative X direction. So here, to bring the value of B to 0, a magnetic field reverse of H is required to apply. So the value of H which brings B to 0, look, here when we will increase H to the negative X direction, then we will see the value of B will be 0. So the value of B which brings the value of H which brings B to 0 is called coercive force. Okay, coercive force, and this phenomena is known as coercivity, which is, look here at this point, and the point C, the value of B becomes 0. So this phenomena is known as coercivity. Now the value, now in the reverse direction, if the reverse magnetic field is, look here, if the reverse magnetic field is made to 0, again reverse magnetic field, that means H is 0, but we will see the net magnetism in the ferromagnetic sample will not be 0, rather there still exists some magnetism in the opposite direction. So that is also known as retentivity. So you can see in this at this point there still exists some magnetism in the ferromagnetic substance. So that is also known as retentivity in the opposite direction. So now if H is increased and brought to its initial position, look, if H is increased and brought to its initial maximum value, then the value of B will be increasing along this curve, that is along this curve way, and attains the value of attains a value which will be saturated at the point A. That means above this point A, the value of B will not be increased. Okay, so when again the magnetizing force will be increasing, we can see the magnetic flux density that is also will be increasing, and at point A it becomes saturated. So this is a cyclic process, like a that means that's why it is known as, this phenomena is known as hysteresis. So here the curve O, A, B, C, D, E, F is known as hysteresis loop. So we can give the definition of hysteresis loop. That means after magnetizing a ferromagnetic substance by applying a magnetic field, then to demagnetize, if demagnetize it, if the applied field is withdrawn, it is seen that it does not demagnetize easily. So look here, by applying magnetizing force, we can see the ferromagnetic substance magnetic field intensity will be increased. But when the magnetizing force becomes zero, that time the ferromagnetic substance will not lose its magnetism fully. There still remains some magnetism. The way the magnetism of the substance increases while applying a magnetic field, the magnetism does not decrease in the same way while the magnetic field is withdrawn. This apathy of demagnetization of the magnetic substance is called hysteresis, which is shown by this loop. So dear students, today after this, and this is the last topics of your chapter, that is chapter 4. The name of the chapter is Magnetic Effect of Current, Electricity and Magnetism. So after finishing this chapter, I will start very soon a new chapter. Till then, stay safe and stay strong. Here the full process of hysteresis loop is written in this box. You will read it, and it is also given in your book. You will get also there. There is a moral for you. You are stronger than you know. So goodbye everybody.